Hi there, this is GCSE Physics. This is Atomic Structure Lesson 6, and the title is Radioactivity, Alpha, Beta, and Gamma Decay. And the objective is to solve decay equations for alpha, beta, and gamma radiation. Remember, at any point, if you wish to make any notes, please pause. Let's move on. So first of all, what is alpha decay? So alpha particles consist of 2 protons and 2 neutrons. They are emitted by some of the isotopes of the heaviest elements. And remember that these decays occur because an atom wishes to become more stable. That symbol there, this one, is the symbol for alpha radiation. Okay, let's look at an example. So this example is the decay of uranium-238. So we've got uranium-238. So uranium-238 is the mass number, and the 92 is the atomic number or the proton number. So it decays by alpha. So we've got the plus 4 alpha. And then what we need to do is just make sure that the numbers add up. So we've got 238 to start with. So if we decay by alpha, which would be a mass number of 4 because it's 2 protons and 2 neutrons, that would leave us with 234 mass number for TH, and TH is thorium. So at the bottom we've got 92, so that's the proton number, remember. So an alpha particle is 2 protons and 2 neutrons. So at the bottom we would have 2, which is 2 protons. And then to balance each side of this equation, we need to have 92 on the left and 92 on the right. So whatever element this is must be 90. Now, in an exam, you'd be expected to be able to figure out the numbers, but not know what the element, the daughter nuclide, or the element that it turns into actually is. So in an exam, that might simply just be, an X. You wouldn't be expected to know that uranium decays into thorium. Okay, but you would be expected, if the numbers were blank, to be able to fill the numbers in. So a couple of notes. So uranium-238 decays to thorium-234 plus an alpha particle. So a couple of notes, the mass and atomic numbers must balance on each side of the equation. So 238 on the left-hand side is equal to 234 plus 4 on the right-hand side. And the 92 on the left is equal to the 90 and the 2 for the atomic number or the proton number on the right-hand side. The alpha particle, if you wish, which is less commonly done, can be illustrated or notated as helium-42. The typical one is this, the alpha particle. Okay, let's move on. What I would like you to do then, using your newfound knowledge, is to try and complete this question. So if you want to pause and attempt this, that'd be great. So question, show the equation for plutonium-239, Pu, decaying by alpha emission to uranium, atomic number 92. So it decays by alpha emission, so it should look something like this. So you've got plutonium, mass number 239, shown in the question. It's got 94 protons, as it decays to uranium with an atomic number of 92. So the 94, you should know that if you've got 92 on the uranium and it's decayed by alpha, alpha means that you've lost the 2 protons, which would mean that you've got 94 protons to start with. And in terms of mass, you've got 239 at the beginning. It loses a mass of 4, which would result in a mass of 235. Another way of looking at it, which I'll do with the pen, so if you started with plutonium 239.94 and I were to lose an alpha particle, I could, make sure that's a U, I could write the plus alpha first, and we know that an alpha is 2 protons and 2 neutrons, so it's got a mass number of 4 and a proton number of 2. Then fill in the blank numbers. So on the right hand side, we've got to make 94. So if we've got 2 already, we need 92. Plus 2 is 94. And the top will be 235, because 235 plus the 4 on the right next to it would equal the 239. Now the element you would not need to know. In the question it says that it decays into uranium, which is fine, so you could put a U. In an exam, if it didn't, you could just put an X, which would be fine. Okay, let's move on. So what is beta decay? Beta particles consist of high-speed electrons. They are emitted by isotopes that have too many neutrons. One of these neutrons decays into a proton and an electron. The proton remains within the nucleus, but the electron is emitted as a beta particle. Okay, if you wish to make any notes, please pause, and please do so. So beta decay is where a neutron decays into a proton and an electron and fires the electron from the nucleus. It's a very commonly asked question, comes up all the time. What is beta decay? Don't fall into the trap where it says what is beta decay and just say, oh, it's a fast moving electron. Beta decay is actually asking for the process behind where the electron comes from. And that's what's written down. So please make some notes. Okay, let's move on. So here's an example, the decay of carbon-14. So we've got carbon, it's got a mass of 14 and a proton number or atomic number of 6 at the bottom. And this is how we write it. So beta, or beta decay, is where a neutron turns into a proton. So if a neutron turns into a proton with an extra proton, which is why the 6 has turned to a 7, but the mass number will remain the same. And we signify beta decay with this symbol, which is beta minus, and then the numbers just have to add up to the original. So if we've got 7 on the right hand side, to make 6 we need to minus 1, so 7 minus 1 equals 6, and then 14 plus 0 will equal the 14. So get that down as an example. So this one, carbon-14 is decayed into nitrogen-14 plus the beta particle. So a couple of notes. The beta particle, being negatively charged, has an effective atomic number of -1, as shown in the question. And the beta particle can also be notated as 0e-1, which isn't typical. Typically, this is the one that we use. Okay, let's look at an example. So here's a question. Show the equation for sodium-25 Na, atomic number 11, decaying by beta emission into magnesium. So if you want to pause and have a go at this, and then I'll take you through the answer. So there we go. So essentially we had, I'll do this with the pen, so sodium 25, and it says atomic number 11, and it decays by beta decay. So if you just put an arrow, you can put the beta in first. Now beta, you should know, is 0-1. Then we just need to make the numbers fit. So we've got on the right hand side, we've got something -1 to make 11, so that's obviously 12. And then something plus 0 to make 25, so that's obviously 25. It just so happens that it's said to you in the question that becomes magnesium Mg. If it didn't give you the element that it becomes, then you could just write X in an exam. But let's use Mg, because that's what's given. And there we have it. So hopefully that went okay. Okay, let's try another example. Next up, gamma decay. So gamma decay is the emission of electromagnetic radiation from an unstable nucleus. Gamma radiation often occurs after a nucleus has emitted an alpha or beta particle. So an example, cobalt-90. It's got a mass number of 90 and an atomic number or proton number of 27. So it decays into cobalt, doesn't change, plus a gamma. So gamma 0, 0. Basically, a gamma decay follows a decay of alpha or beta, where the thing that's produced, in this case cobalt, has excess energy, and what it does is give off a gamma photon or gamma radiation to reach a more equilibrium position, okay, to lose that excess energy. So cobalt-90 with excess energy decays to cobalt-90 with less energy plus gamma radiation. Okay, let's move on from there, do a little bit of consolidation, sorry. Remember, at any point, if you need to pause and make any notes, please do so. So we've got changing elements. Both alpha and beta decay cause an isotope to change atomic number and therefore element. Alpha decay also causes a change in the mass number. So if you want to try and fill this out, that's great. Then I'll take you through the answers. So decay type alpha. So what happens to the atomic number? Atomic number will go down by 2, and the mass number after alpha decay will go down by 4. Remember that an alpha particle is 2 protons and 2 neutrons, so it has a mass of 4 and an atomic number or proton number of 2. So about beta, we've got to remember what beta is. So beta is where a neutron turns into a proton and an electron and fires the electron from the nucleus. So the atomic number, the number of protons, will actually increase by 1. The mass number, however, would undertake no change because a neutron is turning into a proton. So mass number is the same, atomic number goes up by 1. For gamma, the atomic number, there's no change, and also for the mass number, there's no change, as we spoke about previously. Okay, let's move on to some questions. So here you go, complete the decay equations below. So if you want to put the missing numbers in, and then I'll take you through the answers. The first one, complete the decay equations to show. So we've got Fe, which is iron, 59 and 26. So we've got beta decay, and CO, which is cobalt. So the cobalt will be 59, because 59 plus 0 is 59. And then 27 and -1. So you have to remember that the beta minus is -1. And then obviously 27 minus 1 gives us the 26 for the iron. So let's look at the next one. So the 88 we would get from knowing that the alpha is 42. So 86 plus 2 would give us the 88 which we started with. And then the alpha particle, and we would have the 224 radon. So obviously, sorry, radium, and then the 220 radon. 220 plus 4 would give us the 224 that we started with. And then the last one, the mass number at the beginning. So we've got 16 and 0 on the right hand side. So on the left hand side we've also got 0. And then the missing element symbol will be oxygen, 16.8, and beta minus. If you didn't get the oxygen, don't worry, that's fine. Hope that went okay. Let's finish with a consolidation exercise, if that's okay. So you can pause and have a go without the keywords. I'm going to put the keywords on in a second. So if you want to pause with the keywords, please do so now. And then I'll take you through the answers. So when an unstable nucleus emits an alpha particle, its atomic number falls by 2, and its mass number falls by 4. Beta particles are emitted by nuclei with too many neutrons. In this case, the atomic number increases by 1, while the mass number remains unchanged. So the next bit, just to get a bit of a starter on this one, background radiation, which we're going to move on to in subsequent lessons. Background radiation is mainly due to natural sources of ionizing radiation, such as radon gas that seeps out from rocks in the ground. So we're going to move on to this section quite extensively in a couple of lessons, where we're going to learn about what background radiation is, what sources background radiation comes from, and then radon will go into quite a bit of detail exclusively on why that's such a major contributor to background radiation. So I hope you found that useful. Next lesson we're going to do some decay equation practice questions, and thanks for watching, and I'll speak to you soon.